Welcome to The Explainer. Today, we're going to pull back the curtain on the digital world and look at one of the most fundamental building blocks of all computer memory. It's a tiny, absolutely ingenious circuit called the flip-flop. So think about this for a second. We all know computers are basically just billions of super simple on or off switches. But how? How do you get a bunch of switches that can only say yes or no to actually remember something? How can it hold on to a piece of information even for a split second? Well, the secret sauce is a concept called a sequential circuit. You see, unlike a simple light switch on your wall, its output isn't just about what's happening right now. It's also based on its own history, on what state it was in a moment ago. And that, right there, is the very essence of memory. To really wrap our heads around this, we need to start with the most basic one-bit memory element you can possibly imagine. So, let's meet the computer's memory switch. This little guy is a flip-flop. Now, engineers have a fancy name for it, a bistable multivibrator, but that's just a long way of saying it has two, and only two stable states, high, which we call a 1, and low, which we call a 0. It can flip into one state and just hang out there, or flop back to the other and stay there. It's literally a one-bit memory cell, and here's the golden rule. It has two outputs, Q and its exact opposite, Q bar. They are always complementary. If one is 1, the other one absolutely has to be 0, no exceptions. So let's start with the OG, the simplest version of this idea that was cooked up right at the dawn of computing, the set-reset or SR flip-flop. Okay, so how does it work? It's pretty straightforward. If we send a little pulse to the set input, the output Q becomes a 1. If we send a pulse to reset, the output becomes 0. Simple enough, right? And what if both inputs are 0? Well, the circuit just holds on to whatever state it was in last. It's remembering. But, and this is a big but, what happens if we tell it to set and reset at the exact same time? You break it. You get an invalid state. The circuit's logic just completely short-circuits itself. Both outputs, Q and Q bar, can become 0 at the same time, which completely violates that golden rule we just talked about. This state is forbidden. It's a critical, show-stopping design flaw. So, right out of the gate, engineers had a real problem to solve. How do you build a reliable memory cell that doesn't have this built-in self-destruct button? And the solution? Oh, it is just an elegant piece of engineering. The JK flip-flop. For set, reset, and remember, it works exactly the same as the old SR version. But it takes that broken, useless, invalid state and gives it a brand new, incredibly useful job: toggling. Now, when both inputs are 1, the output just flips to whatever its opposite was. They literally turned a bug into a feature. Problem solved. Or was it? Because in solving one very obvious problem, a brand new, much more chaotic one popped up. This one is called the race around problem. So here's what happens. These circuits don't just run wild. They wait for a timing signal, a clock pulse, that tells them when to do their thing. Well, in the JK's awesome new toggle mode, if that clock pulse stays on for just a little too long, the output flips. But that new output immediately feeds back to the input and causes it to flip again and again and again, totally out of control for as long as that clock pulse is active. So the clock pulse goes high and bam, the output toggles to 1. But that signal races right back around to the input, and before the pulse is even over, bam, it toggles again to 0. And then back to 1. This can happen thousands, even millions of times in a tiny fraction of a second. It's just total chaos inside the circuit. So when the clock pulse finally ends and this crazy storm stops, what's the final state? Is it a 1 or a 0? You have absolutely no idea. The output is completely unpredictable, which, for a memory circuit, makes it completely useless. This was a huge problem, and the solution that finally tamed the JK flip-flop is honestly one of the most clever designs in all of digital electronics: the master-slave configuration. The whole thing is a two-step system. The best way to think about it is like a secure airlock with 2 doors. Okay, so when the clock signal goes high, the first door opens. The master flip-flop inside looks at the inputs and figures out what it's supposed to do. But, and this is key, that second door, the one to the final output, stays locked. Then, when the clock signal goes low, that first door slams shut, locking the master's decision in place. Only then does the second door open, letting the slave flip-flop copy what the master decided and update the final output. This makes sure the output can only change exactly once per clock cycle. It completely stops the race-around condition dead in its tracks. So, what a journey, right? We've gone from a simple switch to a flawed design to a chaotic circuit, and finally, to a rock-solid, reliable 1-bit memory cell. Now, let's talk about why this whole journey actually matters so much. It matters because everything digital is built on this foundation. You group a few of these flip-flops together, and you get a register that can store a number or a letter. These registers act like little holding pens for data, letting your computer's brain move information around without losing it. They're at the very heart of any circuit that needs to count things, and they are the absolute basis of the fastest type of computer memory, static RAM. So just how many of these little problem-solving circuits are all around us? Well, just think about this number. That's right, billions. From the main processor to the graphics card to the memory chips, the device you are using at this very moment contains billions of these tiny circuits, each one a little monument to this journey of innovation, flipping and flopping away to hold the ones and zeros that make our entire digital world possible. So we've seen this incredible evolution, from a single switch that couldn't make up its mind, to a clever circuit that literally raced itself into chaos, and finally to the elegant master-slave design that became the bedrock of all digital memory. It really makes you wonder, doesn't it? What seemingly impossible problem is the next tiny circuit being designed to solve right now?